Okay, so I think the screen is visible to all of you.
Yes,
If
ma'am.
not, let me know. Yeah. All right. So in the last class, we had seen that what is input queuing, what is the architecture of a router, and what is longest prefix matching. So we were basically looking at if there is a packet that comes with a particular header, that is a IP address, that is having an IP address for the destination. So how do we find out what is the corresponding output port? And that is done. One main way of doing that is using the longest prefix matching. Okay. So today, so that was part of the input buffer. So we had seen that here there are three modules. Let me just turn on the laser pointer. Yeah. So in each input port, we had like these three modules which are here, each one of which is basically working with different layered functions. Okay, so physical layer functions, data link layer functions, and then network layer functions. Okay, so with respect to the network layer functions, one of the functions was prefix matching. That is, you get the IP address and then find out that which corresponding output port to go to using the in the table in a table there is different prefixes which are given. Whichever prefix matches the longest with your IP address, you simply send the packet or forward the packet to that particular output port. That's what we had studied in the last class. Now, today we are going to see, or we are going to study about switch fabrics. Okay. So as we know, switch fabric is this middle junction which is there between the input ports and the output ports. The task of the switching fabric is to transfer these packets from the input port to the output port, corresponding output port. Okay. So this is the task of the switching fabric. Now, what should be, so see, there are so many input ports. We have like n input ports and there are n output ports. Okay, so there should be a given rate at which the switch fabric will be transferring the data from the input port to the output port. So that is defined, or that is known as switching rate, and that is defined as the rate at which packets can be transferred from the input port to the output port. Okay, so now if you have multiple input ports and multiple output ports, you can simply find out what is the switching rate, and then you can finally see that what would be the throughput of the given switch fabric. Okay, now this switch fabric, or sorry, this rate is basically this switching rate is basically measured as a multiple of the input output line rate. So if you remember in the last class, we had talked about this line rate of an input port, that is how fast your packet which is arriving at the input port is moving through this input port. Okay, so that line rate is also a measure of how fast the data can actually be transferred. And then of course you have the switch fabrics transfer rate. Okay, now if you have this line rate as R, and if you have this n input ports, then the switch fabric switching rate should ideally be n times of R. Okay, ideally whatever number of input ports are there, and whatever and however fast they are transferring the data, the switch fabric should be able to transfer the data at least that much faster to the corresponding output ports, right? So that is why the switch fabric switching rate is given out that ideally it should be n times of R. Now, of course, it is not possible to have this ideal switching rate, right, n times of R, because we know that it is a hardware based module, and it is definitely going to be costlier if we are going to have a very fast switch fabric. Okay, so this part or this module of this chapter, I will give you a little bit of history on the switch fabric. Okay, so earlier when switch fabrics were being made, there was nothing like a simple module that is being made and then that is put into the input ports or connected with input ports and output ports, and then that module is helping to transfer the data from. So there were different generations of switching fabric that came into picture. Okay, so this part is basically in the next advanced course, which is topics in networks. Okay, but today because we are just having an overview of what is switching fabrics and what are the different types of switching fabrics, I'll just give a quick overview of these different generations of switch fabrics. Okay, so we have already learned about switching rate. Now we are going to read about the different types of switch fabrics, which as I already told you, they were called as different generations of switch fabrics. First generation, second generation and third generation. These are the three generations. So the first generation of switch fabrics was something like this. That means the switch fabric itself is simply a memory. Okay. So what does this mean? It is basically that you would just put a computer in between or connect a computer in between different input ports and output ports. Whatever memory it is having, that was the bandwidth or the bandwidth of that memory that was being used for transferring data from the corresponding input port to the corresponding output. Okay. Now then the second generation came into picture, which is the bus architecture. And so you have just a shared bus, single shared bus between the input ports and the output ports. Okay. And then we have the third generation, which is having an interconnection network between the input ports and the output ports. We will read about these three in detail in the next slides. So let's start with first generation routers. Okay. So as I already told you, it is like, just putting a computer between an input port and an output port and using the computer's memory as the switch fabric. Okay. So that means it is under the direct control of CPU. Okay. So what would happen? The packet will be copied to the system's memory and then it will be transferred to the output. So the speed with which the data can be transferred via this memory is limited by how much ever bandwidth this is having, right? So that means it is the transfer of data from or the transfer rate of this switch fabric is basically limited by the memory bandwidth. Okay, and so this is the memory bandwidth, and also two bus crossings are there per datagram, right? From input port to the corresponding output port. So you have two bus crossings. That means you are using this system bus to transfer the datagram, right? So the packet comes to the input port, it's copied into the memory, and then it is transferred to the output port. So there are two bus crossings here, and it is limited by by the memory bandwidth that is available. Okay, so this is what it is. It is copied at the memory, the packets, and then you are transferring it. Okay, so these, see, I am calling them packets just because it is a simple entity with a limited size, but it is actually a datagram, right? Because we are working with network layer, we are actually working with datagrams just for the sake of easiness, I'm just using the term packet here. Okay, all right. Now, excuse me. Now we have the second generation, which is switching via a bus. So as I told you, so instead of having a memory bandwidth in between, so what was happening? It was copied and then again it was being transferred. So the amount of accesses, the delay also correspondingly that gets increased. So in order to overcome that, this shared bus concept was put into work. So what would happen that there's just one shared bus and all the data is being transferred via this one. Now what would be the problem? So everybody would try to contend for the bus, right? Because if everybody transfers data at the same time on the shared bus, of course there will be collision and there can be a loss of data. Whereas if there's an exclusivity of getting the bus and then transferring the data to the corresponding output port, in that case there will be a contention to get the access to the bus, right? So bus contention was a challenge, and on top of that, whatever the bus bandwidth is, the switching speed will be limited by that. Okay, so this is one problem that we were having with shared bus concepts. Okay. The next one is that switching via interconnection network. Okay. So this is the third one, or it is also known as the third generation. And in this case, all of the issues that were there with memory and shared bus concepts, those were tried to handle in this particular scenario. So as you can see here in this diagram, it is nothing but a crossbar. Okay, so it's like a grid kind of a structure, and there are the interconnections in between. Okay, so if you want a particular path, you can. So these are basically switch small connections or switch kind of things. If you want the connection to be there, you put this and make it a connection. Otherwise, you just flip it up so that there's no connection to that path. Okay. So in this case, what will be the advantages? Actually, you can get a path from, you can get multiple paths from different input ports to the output ports at the same time, right? So here, this guy can transfer the data to this guy, whereas input port 2 can send data directly to input port 1, okay, at the same time. So this is one of the advantages that we get. Am I audible? Hello?
Yes, ma'am.
Yes, ma'am.
Okay, I'll just mute for a minute. Okay, I just want to drink some water and come back. Am I audible?
Yes, ma'am.
Hardik, you have something to say?
Ma'am, you are connecting input ports to output ports via multiple networks. We might as well connect every input port to every output port. Why don't we do that?
Then if you connect all input ports to all output ports, so how will you actually make the connection? So you are saying that from input port 1, you will have a connection to n connections to n output ports.
It seems feasible for less number of input ports. Is all I'm saying.
No, no. Look, hmm, how will it look like? Let me see. Acha. So here you are saying you will remove the switch fabric. Okay. Now, suppose there are n input ports here. So you are saying that you will have connection from each input port to the output port. But there can be a packet that can come from this input port and it wants to go to this output port. So that means for each input port, you must have a connection to all the n output ports, right? So can you see the complexity here now?
Yes, ma'am. So there will be like n square connections.
Exactly. You have to maintain so many connections in that case.
So basically, what we are doing in this interconnection thing is it is midway between this and like every connection between
Yes, these are the
ports.
two different modules, a set of input ports, a set of output ports. This guy is the connection between them.
Right.
Okay.
Okay. Yes. Fair enough. Thank you.
Where is it? Yeah, bus. Okay. So the crossbar switch is basically a grid kind of a connection where you simply can have multiple paths between an input and an output port, and you can have multiple connections and different paths. Now, what can be the problem? See, there are first of all n cross n connections which are required. Okay, so it becomes a little complex in any ways. All right, so this is something as you were talking about. I forgot your name. Who just raised the question? Um, it would look something like this, where you are talking about connecting all the input ports to all the output ports. Okay, but here it is nicely done with the help of a crossbar. Okay, so the complexity and the complexity of the hardware as well as the handling, that is which input port to which output port and then taking which path to do that, that increases manyfold. Okay, but still it seems to be a better procedure, the crossbar connection. So, what can be done if we still want to have, large number of input ports and large number of output ports uh, added to a router, and still want to have a better or faster switching rate? Okay, so instead of having just this one connection, like the input ports, output ports, and then just having one single grid connection between them, which will increase the complexity to n cross n. Instead of having that, what are you going to do? You are simply going to have multiple crossbar switches and then connect them together with different input ports. Okay, so this is known as multi-stage crossbar switch. See, this and all, these are all advanced concepts, but I'm just giving you an overview of this. In the advanced courses you will definitely learn about how this work, what should be the value of these multiple stages in between and all that. I'm just giving you an overview and just a history of what is happening and what has already happened in the history related to switch fabrics. Okay, so these are the set of input ports, these are the set of output ports, and the in between, instead of having just one single switch fabric having a grid kind of a connection, you simply have small modules which are smaller switches and which are taking care of transferring the data from different parts of these input ports, then forwarding it to the corresponding output ports. Okay, these are known as multi-stage crossbar switches. All right. Okay. So this crossbar switch, it basically exploits parallelism. How it exploits it? It fragments the datagram into fixed length cells on entry and switches cells through the fabric and reassembles the datagram as it exits. Okay. So this is what's happening. Yes. Alright, so you fragment the datagram into fixed length cells. It enters and then it is transferred over the fabric and then finally it is reassembled as a datagram at the exit. Okay. Now, if you further want to increase the complexity, but you want to also increase the throughput in the end, so what you can do? You can do switching via interconnection networks. Okay, so this is nothing but these are different switching planes, okay, which are kept in parallel. So each input port is having a connection to different fabrics, different fabric planes. Okay, so there are 8 total fabric planes in between, and there are n number of input and output ports. Each one of them is connected to a single fabric plane. Okay, so these input ports are, each input port is connected to 8 fabric plane and they are further connected to each of the output ports. What's happening with this? So you are basically having a lot more faster or a better chance of transferring the data a lot more faster than what was happening earlier, right? So there's a speed up and a scale up that can be used via parallelism. Okay, all of these planes are basically providing a large amount of parallelism here, and then that data can be transferred over the corresponding output port. Okay. Now, why do we need all these things? It may not make sense right now because you might be thinking that, okay, only one packet is getting to the input port, then, or whatever number of packets is getting to the input port, they are coming one by one. So, why do we need all this kind of parallelism and what is happening? Then it is just simply increasing the complexity. We will get into that in the next slides. Okay, that why we are doing all of these things. So this is an example of a Cisco CRS router diagram here. Okay, so this you can take a look later on. What is the configuration of this? Now let's get to the question that was just raised. Okay, that why we are doing all of these things? Why do we need such parallelism? Why do we need it to be faster? Okay, faster we all know that switch fabric needs to be faster because there are n input ports and they are transferring data. If the rate of data transfer becomes too high and the switch fabric is not fast enough, then of course there will be queuing, and then with that we know that when there is a large amount of queuing, then we do have packet loss. Okay, and delay is also increased. So what's happening with input port queuing? All right. So um, I just told that if the switch fabric is slower than the input ports combined, then queuing may occur at the input queues. Okay, so you have n input ports, their line rate is R, and if your switch fabric's rate is less than that, transfer rate is less than that, then of course there will be queuing at the input ports. Okay, now so why this bar is not going? Just a second, this bar should go. Okay. So you have this switch here. Now there are packets. The red colors, the colored ones, they are supposed to be going to the output port 1. The blue colored one, which is supposed to go to the output port 2. And there's the green colored one also. Alright. Now, if we are having queues here, What would be the problem? See, there can be packets which can go to the same destination or which would want to go to the same output port. Here destination means the corresponding output port. Now if they both want to go to the same destination, then in that case there will be a contention to get to that particular output port. Now this is called as output port contention. Okay. Now what is it going to result into? What's going to be the result? So if there is a contention, so only one of them gets the chance to transfer at a time, right? To the same destination, of course. So now what would happen? Suppose this first guy, that is the one which is at input port 1, that guy gets the chance to transfer. So this first red packet gets transferred to the corresponding output port, as you can see in this diagram. Okay, this guy gets the chance. So this is at time t equals to 1. Okay, at time t equals to 1, there was this problem that happened, that is two red packets wanted to get to the corresponding output port and they started contending. At time t equals to 2, what happened? First input port 1 got the chance to transfer and it transferred the corresponding packet to the corresponding output port. And now this red packet, that means the one which was at input port 3, this one will get the chance to transfer the packet to the corresponding output port. Alright. Now what was the problem that happened here? Look at this green packet here. At time t equals to 1, this green packet had a fully available path to the corresponding output port. It could, if there was a path, then I mean, of course, the path was available. But if it was ahead of this red packet, then it would have been easily gone to the corresponding output port, and even the entire switch's throughput would also have increased because it would have transferred all these three packets. But now what happened? Because there was a contention here, because both the packets, the packet which was ahead of this green colored packet, there was a contention related to that. So because of some other packet which was ahead of this packet, it got stopped. It could not get transferred to its destination output port, even though there was a path available. This kind of a contention or this kind of a situation where a packet gets blocked because of some other packet which is ahead of it in the queue or which is in the head of the queue, that is known as head of the line blocking. Okay, this is one feature of input queue. All right, I hope this is clear. This is a very important concept, so please um, take a look at this. Okay, now we are done with input ports, we are done with switch fabrics. Now we are going to the output port queue. Okay, so this is the corresponding, this is how the output port looks like. So your packet will move out from the switch fabric. This is your queue at the output port. Then you have the corresponding link layer protocol, and then you have the physical layer protocols, which will basically send the data to the corresponding medium. Okay. Now, why do we require a buffering at the output port? Okay. Now, we require this because when datagrams will arrive much faster from the fabric than the transmission rate of this particular output port. Okay, so we know that the link transmission rate, okay, that is given by R here. Now, if the switch fabric has a much faster transmission rate, then there will be a queuing here. So that is why output port is having a buffer so that it can just keep them queued and then transfer the packets as per its line rate, which is given by R here. Now there is a problem in this case, that if there is a buffer overflow kind of a situation, then you would have to drop the packets. Okay. Now imagine that you are a service provider or network service provider. If you treat all the users in the same manner, then you are not a good businessman. That means you are going to lose a lot of customers, big customers. So whoever is the big customer, for them you have to have a better and bigger priority than all the other customers who are not paying you that much. Okay. Now when all the sets of packets are coming out of a particular router, inside the router there's the switch fabric, and when all the packets are coming one by one, now if at this place at the output port there is a buffer and there is a chance that the buffer overflow is going to happen, then what's the first thing that you are going to decide? You have to decide that which packet should I drop, because definitely there's going to be a drop of packets because you don't have that much of buffer space. So depending upon how prioritized packets are there or how much prioritized customers you are having, so depending upon that, you will simply drop the packets for those customers whose packets do not have that much of priority, right? So you must have some kind of a packet drop policy for this. Okay. All right. Now, now there's the other part. So as I told you, that priority of customers and what kind of um, plans they have taken, okay, what is the demand that they have put, depending upon that you try to serve the customers. Okay. Now for dropping, you have already considered that prioritized customers packets will not be dropped first. You will drop the non-prioritized customers packets, right? Similarly, there is a queue here. Okay. In general, what we think that from this queue packets can be taken out one by one in an XCFS manner. It might seem so, right? That the naive answer would be that, yeah, there are packets in the queue, we'll transfer them in FCFS manner. But if you have prioritized customers where they are asking for a good data rate, and also the application that they are working with, that is also having a very high or very low delay bound. So in that case, you must transfer the packets as fast as possible. So for that, at this juncture, there is also a decision that needs to be taken. That is, how will you schedule these packets out of this queue? Okay. So for that, we need to have several scheduling disciplines, which will tell us that which packet to transfer after which one. Okay. All right. So, okay, so we have a term called network neutrality here. We will read about this, but I would like to ask you, have you guys heard of the term network neutrality? I hope so, because there was a lot of buzz about it on the social network for a long time. So, any idea of what is network neutrality?
Yes, ma'am.
Yeah, what do you understand about it?
It's a guarantee that ISPs won't be able to control the your bandwidth depending on which sites you're visiting. They must give you the same bandwidth for all sites, I believe, or all hosts. That is it.
Yeah. So basically, you want to, the customers want to be treated in a neutral manner, right? So that is what the network neutrality basically means. So essentially, network neutrality would be that that ISPs should not have a control of how the or how to treat the customers depending upon what are they saying, what are they doing over the internet, and how much they are paying. Okay, so that's what network neutrality is. So let's see. But first, let us see what's this output port queuing and how does it work. All right. So now there are see there are packets here, as we had seen in the input port queuing scenario also. There can be several packets which are coming to different input ports, which want to go to the same destination. Okay, so in that case, there will be too much contention for the same output port. So if the switch fabric is fast, in that case, and the output port line rate is not fast enough, in that case, it will result into buffering at the output port. Okay, so that's what basically output port queuing is. And if the buffer size is small enough, then there it will lead to a buffer overflow. Okay, so first, how much should be the buffer size then? Okay, we have to find out some buffer size for the output port. So as per the RFC 3439, okay, this is a request for comments document, and according to this RFC, the average buffering should be equal to the typical RTT. Okay, that means what's the estimated RTT that can be, I mean, that is basically taken to transfer a packet and get the corresponding acknowledgement. So the typical RTT times the link capacity. Okay, so this is just an example that is given. So suppose your RTT is 250 milliseconds and you have the link capacity as 10 Gbps, then your average buffering should be this much, 2.5 gigabit. So more recently with research, it has been found out that if you have n flows, then your buffering should be equal to RTT times C divided by root over of n. Okay. Now, if I have, now still there is a challenge, right? If I have too much of buffering, in that case, I will increase the delay for all the packets, right? And if suppose in the network I have a very long RTT, okay, so in that case, what would happen? That it will still give a poor performance for the real-time applications, okay. And of course, we will have, I mean, if there is delay-based congestion control, then in that case, it will just simply fill the buffer, okay. Now, let's get to buffer management. So this is basically an abstraction of this. Okay, if you have learned queuing theory, any of you in your uh, other courses, then you might find it similar to this. But if not, still I will simply say this is just a queue, right? This one with several packets here. Okay. Now we are making an abstraction of this here. Okay. How are we making an abstraction? There's a switch fabric which is basically transferring the data to this output port. So here we are having the packet arrivals. Now there's actually a physical buffer here which is keeping the packets. So this is the abstraction of that queue here. Okay, it is the waiting area for all the packets that are arriving. Now, after the packet goes out of this queue, then it is being, you know, there are some other protocols which are being used on top of that, and then it is transferred over to the medium. Okay, so there's a rate at which it is being done, which is dependent upon the line rate of the output port. So that abstraction is being done here. Okay, so that is the link, or it is also known as the server. So this has been abstracted as this, the server, and then once that is done, then physical layer protocols are being incorporated over the data, over the given fragment, and then you simply transfer it. Okay, so that is known as the packet departure. Okay, so this is nothing but you have packet arrivals, then packet is getting queued, then it is served, and then there is a departure of packets. Excuse me. Now, when we are talking about, so we just talked about the packets can be dropped, can get dropped when buffers become full. So there are two categories in which packet drops are classified. Okay, so one is known as tail drop, that is drop arriving packet. So here packets will be arriving and you drop these packets which are basically arriving so that your buffer does not get overflowed. And then another is the priority drop or removal of packets. So on the basis of priority, as I already told you, depending upon what is the kind of customers packets you are having, you just drop or remove them depending upon what priority they consist of. The next is marking. Okay. Now, what is it? That is which packet to mark to signal congestion. Okay. So suppose, see, this buffer will be overflowed when there is too much of packets for the same output port, right? So that means the output port is now getting congested. Okay. So it has to basically inform the corresponding source that it is getting congested, right? So when we were talking about congestion control in transport layer, if you remember that we had learned that congestion control information can be either given by the destination in some way or it can be given by the routers in between, or which is known as information sent by the network itself. Okay, so when that happens, in that case, you can send congestion with the help of some particular types of packets which are known as RED packets or ECN packets. Okay. Now the next part that we have studied, that is one is packet drops and another is scheduling of packets. Okay. So when we are talking about packet scheduling, we have already studied a lot about scheduling in operating systems, right? So, and any other course, wherever you start studying scheduling, first thing or the main way of scheduling is FCFS. Okay, so that is one, FCFS is one scenario. We have also talked about priority scheduling, depending upon what kind of customers you are having. Then if we talk about net neutrality, if we talk about being fair with everybody, then in that case, round robin is one scenario. Okay, that is, round robin way of scheduling the packets. Another is weighted fair queuing. So this is a little different. It is a variant of round robin scheduling only, but it's a little different where we are giving weights to each and every connection and then transferring the packets from them. So we will see how it works out. Okay. First, let us see this abstraction. We already know what this abstraction means. If it's FCFS, packets will be simply transmitted one by one from the head of the queue. Okay. Now, this is the priority scheduling policy. Okay. So you are having, so this is an abstraction. Let us see how it works out. We had seen the buffers, right? So look at this abstraction. We had only one queue here. Packet was getting arrived here, and then this was the server, that is corresponding link layer protocol, and then packets are getting departed from the system. From this abstraction, let's take a look at this abstraction. What's happening? Packets are getting arrived. After the arrival, they are getting classified as to what is the priority that the packet comes with. Okay, so depending upon that priority, they are classified into or moved to two different buffers. Here only two different buffers are there, so move to the two different buffers, the low priority queue and the high priority queue, which are further connected to the server here, link layer, corresponding link layer protocol, and then there are departures corresponding. So depending upon what priority the packet consists of, it will be classified, and then that will further impact how it will be scheduled or how the packets will be scheduled further. Okay. Now, how will you prioritize these packets? So you can have or you can consider there are many properties present in the header field. So that one of them, or sorry, just a second. Yeah. So any of the header fields can be used for classification. Okay. All right. Now, if there are too many packets in the same priority class, in that we can use FCFS, right? Whereas in between them, we do have the priority transmission. I hope I'm clear. Between the two queues, high priority queue and low priority queue, we transfer or schedule the packets according to the priority scheduling policy. Okay, but within the same priority queue, we schedule the packets as per FCFS. Okay, right, so this is an example. So we have, like, these are high priority packets and this number 2 is a low priority packet. So you can see that as these packets are arriving, what is the transfer schedule, right? So this is the way they are getting transferred to the medium. Okay. So yeah, it's already 2:57. So I will stop the class here. If you have any questions related to the class, please go ahead and ask. Otherwise, class is over for today.